So, we have learned how to change one thermodynamic derivative to another thermodynamics derivative using Jacobian technique, and I have shown some usefulness in terms of finding out C p minus C v, a general expression of C p minus C v, and also an arbitrary partial derivatives of del g by del h at a constant v, I guess. So, the point is that we can do whatever partial derivative it is using the Jacobian technique, and that will make our life much simpler and will help us also to find out useful quantities. For example, Joule's coefficient or Joule-Thomson coefficient and things like that. So, we are going to go and do some more thermodynamic derivatives, it is called reduction of thermodynamic derivatives. So, we are going to go and do some more reduction of thermodynamic derivatives and see that how we can easily use them and convert them, and we get more accustomed to that. So, we will do some more problems to help you understand that things better. So, today's problem that we are going to do is that problem number 1 has this derivations that derive this following del C v by del v. So, I am going to do it here. So, the first one is prove del C v by del v at a constant t is equal to t del 2 p del T 2 by v. Okay. So, we have to do this problem del C v by del v at a constant t t is equal to del 2 p by del T 2 at a constant v. Now, we will start with the definition of C v. C v is del s by del t, t del s by del t at a constant v. So, we know that. So, once we start with that, we will have to see whether we can get the right hand side expression or not. But before we do that, let us also understand that if we get these things from somewhat from the Maxwell relation or not. So, we write Maxwell relation as P T V, and we see that we can get either del s by del p, or we can get del s by del v, or del p by del t. So, del p by del t we can get though, okay, that is the important thing. So, del p by del t we can get, and we know that from Maxwell relation that del p by del t at a constant v is we have to do this way, is del s by del v at a constant t. Okay. So, that is fine, we have that. However, we see in this particular formula it is just interchange, it is del s by del t at a constant v, but we need del s by del v at a constant t. So, they are not exactly same. So, we will try to see whether we can get that or not. So, now before you get that, so C v definition is this one. So, therefore, if I take one more derivative del C v by del V t, if I do that, then essentially I have to take the derivative of this entire quantity at a constant temperature. Now, if I want to do that, then you see that t becomes a constant. So, t will come out and it will give me del 2 s by del v del t, which by notation means this is a shorthand notation del 2 s by del v del t. The shorthand notation is del s by del t at a constant v, and then the whole thing taking a derivative with respect to v at a constant t. So, that is equivalent to writing as del 2 s by del v del t. Now, we know that s is exact differential. So, therefore, we can write that as del 2 s by del t del v as well. Now, once we do that, we can write t del t del s by del v at a constant t and this whole thing at a constant v. Now, we know that del s by del v t from Maxwell relation is nothing but del p by del t v. and whole thing is at a constant v, which then proves our point that it is nothing but del 2 p by del t 2 at a constant v, and that is what we wanted to show. You see the Jacobian cannot be used in this particular case, because Jacobian will take the derivative to the heat capacities like Cp, Cv and then alpha and kappa T, but here we wanted a conversion of relation, and the way I understood that we have to do this formula for exact differential is when I looked into del p del t as this one, then I realized that, which means that the v and t are interchange, and then I have done that. So you have to do that as well. So now go to the second problem. We have to show that del Cp by del p at a constant t is minus t del 2 p by del t 2 at a constant p. So again I think it is very similar to the problem above. Just let us write Cp as t del s by del t at a constant p, that is the Cp, and we need to do the derivative of this particular one. So we need to do del Cp by del p at a constant t, which means we have to take the derivative of this quantity at a constant t. So t will come out and we will get del 2 s by del p del t. Okay. So again it is a shorter notation, del 2 s by del p del t, meaning first we will take the derivative with respect to t at a constant p, then the whole thing at a constant with respect to p at a constant t. So this is same as, since it is exact differential, as del s del p, which again means that first derivative with respect to p at a constant t, then with respect to t at a constant p. So again we are just going to look at the Maxwell relation S p T v, and we know that del s by del p is del v by del s by del p is del v by del t, we know that. So but there is a plus and minus thing, as you can see from my arrows. So del s by del p at a constant t is del v by del t at a constant p, but with a minus. So it will be t del t del s by del p at a constant t, and the whole thing it is at a constant p, which is t del t, and del s by del p at a constant t is minus del v by del t at a constant p, which is, and the whole thing is at a constant p, which is minus t del 2 v by del t 2 at a constant p. No, but I think it is written, question is given wrongly, it should be v, not p. Okay, so let's go to the next problem. So next problem says that a measure of the results of adiabatic Joule free expansion is provided by the Joule's coefficient mu j. Show that mu j is equal to 1 by C v. So this is nothing but alpha, because alpha is the coefficient of thermal expansion, and this is nothing but kappa t minus p. So I will just write it clearly. So mu j, show that mu j is 1 by C v alpha t by kappa t minus p. So let us see if that is the thing we can show or not. So by definition you see mu j is del T, change in temperature with respect to change in volume at a constant u. So you know, in this particular case we have to use the Jacobian, because we have to bring the u in the numerator. So it is del T u by del V u, I can write that, and then I can take as del T u by del T p, and I have to multiply by del T p and del V u. Now this one left hand side gives us del u by del p at a constant t. So, instead of T p, let us change it to V, because V is good for always u. So, u is a natural variable is V and t. So, let us change it to V. So, instead of p, I will just put V. So, yeah, and that also is good, because here also I am getting V common. So, now we can write that as del u by del V at a constant t multiplied by, I take a minus and then write del V t by del V u, and you know why the minus is, because I switched the numerator positions t and v. Now, del u by del V t, do you remember what it is? So, u is a natural variable, is p d v. Okay, so u is t d s minus p d v. So, that does not help us, because del u by del v at a constant s only we would have got t, but del u by del v at a constant t is given. So, that does not help us. So, we will deal with that later on. So, now just let us continue del u by del v t, or I will put a minus here, and that gives us del t by del u at a constant v. So, which is del u by del v at a constant t multiplied by del u by del t at a constant v inverse, which as you know is C v. So, this is minus 1 by C v del u by del v at a constant t. That is what we got. That is what the Joule's coefficient is. Now, we have to do del u by del v at a constant t. So, we will start with this expression d u equal to T d s minus P d v. Now, we cannot do directly from here del u by del v at a constant t, because t is not a variable here. So, t is just a parameter. So, therefore, we have to divide both sides by dv now at constant t. So, what you are going to get from there is del u by del v at a constant t is t del s by del v at a constant t minus p del v by del v at a constant t, which is t del s by del v at a constant t minus p. See, I am getting back minus p. So, now what else? C v also I have got. Now, I have to just do del s by del v, and that I will now use formula for Maxwell relation. So, S p t v. So, you see del s by del v is at a constant t is nothing but del p by del t at a constant v minus p. So, this also we got, but that does not help us in getting the alpha and kappa t, because in alpha and kappa t we know. So, this much we got. So, now if I just write my del t by del v at a constant u, I have already got minus 1 by C v t del p del t v minus p. Now, I have to prove that this quantity t del p del t v is equal to alpha t by kappa. So, in fact, t is also common. So, I have to prove del p del t, sorry, it was t, del p del t v is kappa t. I will just rewrite it again. I have to prove del p del t v is alpha by kappa t. This is what I have to prove. Then I can prove the whole relation, because everything else is fine with this. Now, we know what is alpha. Alpha is coefficient of thermal expansion. So, del v del t at a constant pressure 1 by V, and we know what is kappa T, right, minus 1 by V del V del P at a constant T. So, alpha by kappa T is 1 by V del V del T at a constant P by minus 1 by V del V del P at a constant T. 1 by V cancels each other, there is a minus sign, we will have to deal with that. Now, del V del T at a constant pressure, del V, no, I will just take by sign, del V del P at a constant T. Now, I am going to use a Jacobian technique, minus del V p by del T p and divided by del, it is not a good way of writing it. So, I will put an inverse, del V t by del P t inverse, meaning just I will just change it, del V p del T p multiplied by del P t by del V t. Now, there is a P t. So, I am going to change that V p del T p, I will going to change, take a minus and say T p del V t. Now, del T p cancels, giving us, and minus minus cancels, giving us del V p by del V t, which is nothing but del P v by del T v, which is nothing but del P by del T at a constant V. So, now I am coming back and I see that I can write this whole expression. I am going to just remove this part. Now, I am going to whole expression I am going to write as T alpha by kappa T minus P, and proved. Okay. Now, for Joule-Thomson coefficient, we have to show that mu j t is equal to minus V by C p. So, this beta is alpha actually, it is just a notational issue, V by C p alpha t minus 1. Now, so Joule-Thomson coefficient is, as you know, that it is change in temperature with respect to pressure at a constant enthalpy. So, this one we have to show as the one that is mentioned here. Since H is held as constant, we have to bring the H in the numerator, and we can do that by taking this, and immediately we need something. So, for example, we need Cp, and you know, just we can just do a back calculation and just find out that what Cp is. Cp is del S by del T at a constant P. So, we need some S somewhere, and alpha is also there. So, yeah, but we need the S and T and pressure. So, that you have to just remember, and also we have to remember our H. H is nothing but H is U plus P v. So, it is du plus P dV plus V dP, and du plus P dV, as you know, is nothing but T ds. So, T ds plus V dP is del H. So, we just keep those things in mind and continue our derivation. So, mu j t is del T h by del P h. We can take the H on the left hand side. So, del H t by del H p. So, now what do you want as a derivative? So, for example, if I do del H by del T, we can do del H by del T at a constant P, yeah, that we can do here. So, for example, we do from this above expression del H by del T at a constant P will give us T del S by del T at a constant P plus, so we are doing with respect to T, right. So, V del P by del T at a constant P. So, that goes 0 So, del H by del T at a constant P is nothing but that. So, we need that. So, we can do this del H T and so we need with respect to temperature at a held at constant pressure. So, that means we need this. So, del H P by del T P, we need that. So, H P is here for sure. So, T P is not here. So, let's write that del T P multiply with del T P and del H P. So, you see I wanted to bring del S by del T at a constant P, and that's why I multiplied with T P in the numerator and denominator. So, now what I am going to see is what is the left hand side. So, I can just take a minus sign and rewrite it del H T by del P T multiplied by del H P by del T P inverse. Left hand side will give us del H by del P at a constant T, and this is going to give us del H by del T at a constant P and inverse of that. Now, this one, what is del H by del P at a constant T? So, let us figure out from that. So, del H by del P at a constant T, I have to take the differentiation again. So, if I do that, this equation, from this equation del H by del let me see del H by del P at a constant temperature is T del S by del P at a constant temperature plus V, because del P will cancel. So, now when you do SPTV, okay, so this will be a little bit longer, not just simple one. So, we will do that more carefully in the denominator. Okay. So, first just write this one. So, we are going to do individually all that. Okay. So, let's do both of them separately. So, let's write that as equation 1 and just write that as term 1 into term 2. Now, term 2 is by definition is very simple, that is del H by del T P inverse. We have shown that that is nothing but del H by del T P is nothing but T del S by del T P, which is nothing but C P. So, this is nothing but C P. So, we can write as 1 by C P. So, we got, as you can see, we got our 1 by C P right there from the term 2. Now, term 1 is minus del H by del P T. So, for that what we need is, we need to write again d H as T d S plus V d P, take derivative with respect to P on both sides. So, del H by del P at a constant T is T del S by del P at a constant T plus V, because del P by del P will be 1. Now, once we have that, we have to use Maxwell relation SPTV, and we know del S by del P at a constant T is del V by del T at a constant P. So, del H by del P at a constant T is T del V by del T at a constant P plus V. Now, what is del V by del T at a constant P? So, yeah, so this and okay, and it will be a minus sign, because you can see that this is going down and this is going up. So, there will be a minus here. So, that will be minus T. Now, what is del V by del T? So, we can say coefficient of thermal expansion multiplied by V. So, this will be alpha V plus V. So, we got the whole thing. So, that means this term 2, our term 1, which is this, is equal to minus of this quantity minus T alpha V plus V, which is going to give us T alpha V minus V, or V T alpha minus 1. Okay. So, now we will put together whatever our answer was. Our answer that we wanted is del T by del P at a constant H is equal to V T alpha minus 1 divided by C P. Did we get that? So, the way it is written is minus V by C P. So, minus V by C P 1 minus yeah. So, I think there is, I have made a mistake with minus somewhere. Let us see, where did I? Let us see. We start with this del T by del P at a constant H. This is not a problem, this part is fine. Here I have interchange P and T. So, this part is fine. So, 1 is having the minus. Now, the side 2, that is T P H P T P. So, 1 by C P is fine. Now, minus del H by del P T. Now, del H by del P T is written here. So, I guess we got the thing right, although there is a difference with just a minus. So, the question was a little bit wrong. So, this is correct, this is correct, the question was wrong. So, this should be plus and not minus. So, I got the answer. So, we will stop here and we will continue.